Hello everyone, myself Manisha. I'm from BTech Engineering Physics. Today I am presenting my microprocessor lab experiment design and implementation of a counter using the 8085 microprocessor and 7-segment display. In this whole presentation, I will take you through the theory, the hardware, the software, the actual experiment, and the results from the very basic of what a microprocessor is all the way to watching the display count 0 through 9. Okay, let me begin with my why we did this experiment and what we set out to achieve. The problem is simple but fundamental. Manual counting is slow, error prone, and impractical for any real digital systems. A microprocessor driven counter solves all three problems. It counts with perfect precision at any speed we program it, and it repeats forever without error. We had four specific objectives for this project. First, the primary objective to design a digital counter that counts from 0 to 9 using the 8085 microprocessor and drive a 7-segment display to show the output in real time. Second, the hardware goal to correctly interface the 8085 with the 8255 programmable peripheral interface chip and connect the 7-segment display to it using the right third, the software goal to write a complete 8085 assembly language program using instructions like move, out, increments, compare, jump at non-zero call, and return, and understand exactly what each instruction does at the hardware level. Fourth, learning outcome to gain a real hands-on understanding of microprocessor input-output interfacing, which is one of the most important concepts in embedded system. All four objectives were successfully achieved, and I will demonstrate this when I show the experiment results later. Before we get into the experiment, let me quickly establish the hardware we are looking with. A microprocessor is a single integrated circuit chip that functions as the entire central processing unit of a computer. It fetches instructions from memory, decodes them, and executes them continuously in a cycle. The Intel 8085 was introduced in 1977. It is an 8-bit microprocessor meaning it processes 1 byte or 8 bits of data at a time. It operates at up to 6 megahertz, though the internal CPU clock runs at a 3 megahertz after internal division. It comes in a 40-pin DIP packages and run on a 5-volt supply. Its address bus is 16-bit, which means it can address up to 64 kilobytes of memory. Now you might ask, why do we still study the 8085 when we have far more powerful processors today? The answer is on this slide. Unlike modern microcontrollers that hide all operation side abstraction layers, the 8085 exposes every signal, the address bus, the data bus, the ALE spline, the read-write control lines. Every single instruction can be traced at the hardware level. This makes it perfect for learning the fundamentals. This slide shows the internal architecture of the 8085 and how it connects to the rest of our experiment. At the center is the Intel 8085 CPU. Inside it, we have the accumulator, which is the main working register for arithmetic and input-output operations. We have general purpose registers, pairs, BCs, DE, and HL. We have the ALU for all arithmetic and logic. We have the program counter, stack pointer, and the flag registers. On the left, the CPU connects to program memory where our assembly code is stored and data memory, the RAM where the data is written and read. On the right, the CPU connects to the 8255 PPI chip through the data bus. The 8255 then divides a 7-segment display. The three buses are critical to understand. 16-bit address bus select which memory or input-output location to communicate with. The 8-bit data bus transfers the actual data. The control bus carries read, write, and input-output memory signals that tell the hardware what kind of operation is happening. This table shows every register we used in this project, its size, and its specific role. The accumulator A8-bit holds the current count value and is used by the increment, move, and out instructions. The B and C register pair 8-bit each are used as general purpose storage, especially for saving the digital counter values inside the delay subroutine. D and E, these are the inner and outer loop counter inside the delay subroutine. H and L, these form the 16-bit HL register pair, which we use as a pointer to segment code lookup table stored at the memory address 2100H. The program counter 16-bit tracks the address of the next instruction jump at non-zero instruction directly from modify the PC to create loops. The stack pointer 16-bit points to the top of the stack. It is used automatically by the call and RET instructions. The flag register, the zero flag inside it, what makes CPI and J and Z work together for our boundary check. When the counter reaches 10, the zero flag is set and J and Z doesn't jump. At the bottom of the slide is a fetch, decode, execute a cycle for the increment A instruction. The PC sends the address to the memory places the opcode 30 on the data bus, the instruction register receive it, the decoder identify it as increment A, the ALU adds 1 to the accumulator, the result is stored back and the flags are updated. This entire cycle takes just 40 states, about 1.33 microseconds at 3 megahertz. Now let's talk about the output side. Why do we use a 7-segment display and not something simpler like plain LEDs? 8085 output binary data. If we connect 8 plain LEDs to an output port, we see a pattern like 0110, and the user has to mentally decode that to figure out what number it represents. That is not practical. More practically, 8 LEDs per digit means 24 input-output lines for pins for a 3-digit counter that far exceeds what a single 8-bit port can provide. And from a power perspective, 8 LEDs at 15 milliamperes each is 120 milliamperes per digit. For 4 digit, that is 480 milliamperes, which is impractical for battery powered system. The 7-segment display solves all of this. The user reads the decimal digit directly, no conversion needed. It uses only 7 pins per digit, and it is an industry standard used in fuel pumps, digital clocks, calculators, medical monitors, and scoreboards all over the world. Let me now explain the physical structure of the 7-segment display itself. As shown in a diagram on this slide, the display has 7 individual LED segments labeled A through G plus a decimal point DP. Segment A is the top horizontal bar, segment B is the top right vertical, segment C is the bottom right vertical, segment D is the bottom horizontal bar, segment E is the bottom left vertical, uh, segment F is the top left vertical, and segment G is the middle horizontal bar. The example on the right shows uh, digit 3. To display 3, we activate segments A, B, C, D, and G in the common anode configuration. The binary code is 10110000, which is B0 hex. Okay, so 7-segment display come in two configuration, and it is critical to know which one you are using before writing any code. In common cathode, all the negative terminals of the LEDs are um, tied to ground. Each positive terminal or anode, it is connected to an output port pin. Logic high, A1, A equals to 1, turns the segment 0. This is positive logic and feels intuitive. In common anode, all positive terminals are tied to plus 5 voltage. Each negative terminal, the cathode is connected to port pin logic low. 0 turns a segment on. This is inverted logic. The ETDIS model we used in this experiment is common anode. So our segment codes are the bitwise complement of common cathode codes. For example, digit 1 in common cathode is 06H. In common anode, it is F9H, the complement. The most common mistake in the lab is using common cathode code as on a common anode display. Every digit appears inverted. A fix is simple complement all segment code. And this is our segment coding table for common cathode mode. This is common cathode mode, and this is for common anode mode. Okay. This slide shows the complete power data from 8085 CPU to lead the segments on the display. The 8085 execute as out instructions. This put the segment code on the 8-bit data bus. The 8255 PPI received the byte on port A. The byte then passes through the 20 ohm current limiting resistance 1 per second and reaches the physical segment pins A through G. The LEDs light up three important pins here. The out instruction mechanics. When the 8085 execute out, the input output uh, M bar line goes high, indicating put output mode. The WR bar line goes low, indicating a write. The port address appear on the lower eight address lines. The data byte appears on D0 through D7. This whole operation takes 10 T states. Um, why a latch is needed? The data bus is only valid for about 100 nanoseconds during a write cycle. The 8255 has an internal latch that captures and holds the byte on PA0 through PA7 continuously until the next write. Without this latch, the segment would extinguish immediately after the instruction complete. The 8085 has no built-in input-output ports. The 8255 programmable peripheral interface provides 24 programmable input-output lines organized as three 8-bit ports, port A, port B, and port C, all controlled by a single chip. Initialization, we write the control word 80H to address 03H. In binary, 80H is 10000000. Bit 7 equals 1, meaning mode set is active. Bit 6 and 5 are 00, meaning mode 0, basic input output. Bit 4 is 0, means port A is output. Bit 1 is 0, meaning port B is output. So single instruction MVI A 80H followed by out 03 configures all three ports as output. The address map on our trainer kit is port A at 00H, drive the segment line A through G to the display. Port B at 01H is used as a data serial line PB0 in a shift register interface. Port C at 02H carries the clock signal PCO. The control word register is at 3H. The efficiency here is remarkable. Just three control pins from 8085, 80A1, and WR bar control all 24 input-output lines of 8255. This is called pin multiplication and is a fundamental technique in hardware design. There are three standard methods of connecting the 8085 to a 7-segment display, and this slide compares them. Method 1 is direct drive. Port A connects through 7 registers directly to the 7-segment pins. Simple, no extra chip needed. This is what we use in our single digit experiment. The disadvantage is 7 pins per digit, which becomes impractical for multi-digit displays. Method 2 is BCD decoder using the 7447 IC. The 8085 output a 4-bit BCD value and the 7447 automatically converted to 7-segment drive signals. Only 4 input-output pins per digit, but you need one extra IC per digit, good for 2 to 3 digit displays. Method 3 is multiplexing. All 7 segment lines are shared across all digits with separate digit select lines controlling which digit is active. Total is just 7 plus 9 and for n digits 61% saving. This is used in all professional multi-digit displays. The trade-off is it needs high-speed software switching. For completeness, let me briefly explain multiplexing since it is a key concept in display designs. For a 4-digit direct drive display, we would need 4 times 7 equals 28 segment pins, far more than one 8-bit port providers. Multiplexing reduced this to just 11 pins, total of 4 digits, a 61% reduction. The segment works by enabling one digit at a time in very rapid sequence. Enable digit 0 send its segment code, wait 2 millisecond, display digit 0 and enable digit 1 and so on a full cycle through 4 digits take 8 milliseconds, giving a refresh rate of 125 Hz. The human eye integrated light over approximately 20 milliseconds. At 125 Hz, the persistence of vision makes all digits appear continuously and steadily lit. Below 50 Hz, you would see visible flicker. One important hardware note, since each LED is only on 25% of the time, the peak current must be 4 times the DC current, which requires a driver IC like the ULN2003. Now let us trace exactly what happens step by step from a binary counter value in the CPU to a visible digit on the display. I will use digit 5 as the example. Step 1, counter accumulator register C holds the value 00000101 in binary, which is decimal pi. This is current count value. Lookup table index. That is step 2. The HL register pair holds the base address 2100H. We add the digit using 5, using value 5 using DAD B, making HL equals 2105H. The instruction MOV A, comma M then loads the byte stored at memory location 2105H into the accumulator. The byte is 92H, the comma anode segment code for digit 5. Step 3, output. The segment code is shifted serially bit by bit through port B pin TPO with clock pulses on PCO. This loads a shift resistor inside the ETDIS display module. Step 4, segment active. The shift resistor drives the segment pins for 92H. Segment A, C, D, F, and G turn on. The display shows the digit 5, and this is why delay is required. Without it, the 8085 completes the entire 0 through 9 cycles in just a few seconds. No human eye can detect individual digits at that speed. The delay shows it to approximately 1 second per digit. A digital counter is a sequential system that advances through defined binary states on each trigger event. There are three main types: an asynchronous counter, also called a ripple counter, where each flip-flop is clocked by the output of the previous one, simple but slow due to propagation delay. A synchronous counter, where all flip-flops are clocked simultaneously, faster and more precise, used in high-speed digital systems. A BCD up counter, which counts from 000 to 1001, that is 0 to 9 in decimal, and then resets to again 4 times 0. This is exactly what we implement in software. Our experiment implements the software BCD up counter using the 8085 accumulator as the count register. The increment A instruction performs the binary addition. The CPI 0AH instruction detects when the count reaches 10 and jump start reset it back to 0. This slide summarizes the 6 logical steps of counting low, and I will go through each briefly. Step 1, move C00 head, initialize the digital counter to 0. This ensures counting always starts from 0. Step 2, shift segment code to display. Look up the segment code for the current digit and clock it into the shift register. This makes the digit visible. Step 3, call delay. Wait approximately 1 second. Without this, the counter is invisible, too fast for the eye. Step 4, increment C. Increment the digit counter by 1. Binary addition in ALU. Step 5, CPI 0AH and GNZ compares the counter with 10. If not, jump back to step 2 and display the next digit. If it is 10, fall through. Step 6, jump start, reset counter to 0 and restart the entire cycle. This create the infinite 0 through 9 through 0 loop. The flowchart on this slide, as we can see, the main loop is starting from 200H, and then we are initializing our 8255 loading digit. Then first we are making sure our a 7 segment is blank initially. Then we are putting our segment code, and then it is showing our uh, code. Now, let me walk through the actual assembly code. The program starts at 200H. The first two instructions, these two instructions, followed by out 03H, initialize the 8255. The value 0H is in binary 1000000. This set all three ports to output mode 0. At address 2004, the label start MVIC00H resets the digit counter to 0. Every time we jump back to start C, it's reset at address 206H, the label blank, as we can see here, the blank. MVID20H begins the display blanking routine. We load 32 decimal, which is 20H, into D. We then loop 32 times sending um, each time sending the bytes FFH to port P, pin PBO and toggling the clock on PCO. This clears all 4-digit points positions on the display before showing a new digit. At address 2018, 2018, we load the base address of the segment table 2100 into HL. We set B to 0, then DADB adds BC to HL. Since B is 0 and C hold the digit index, HL become 2100 plus the digit number. Move AM, uh, this code, move AM. Uh, Loads the correct segment code from address 21 to 201FH. Um, the shift loop, that is a shift loop, we save the segment code in D set E to 8 for 8 bits. Each iteration rotates the byte left using RLC. This brings the most significant bit towards bit 0. We mask with ENI01H to isolate bit 0, output it to port B, then pulse the clock low, then high on port C. This is repeated 8 times to shift all bits serially into the display shift register. After shifting, we call delay at 2035H. The INRC to increment the digit, compare with 10 and either loop back to reset. The delay subroutine begins at 2050H. First push B and push D, save the current value of register B, C, D, and E onto the stack. This is essential because the delay uses these registers internally. If we did not save them, we would corrupt the digit counter in C. We load PC with the outer loop count 3800H and D with the inner loop count 0 triple FH. The inner loop decrements DE using DCXD, checks if DE equals 0 using ORA-E after MOV AD, and loops back with jump at non-zero. When DE reaches 0, the outer loop decrements BC and reloads the inner count. When BC also reaches 0, we pop D and pop B to restore the register, then RET to return to the main program. Uh, uh, The segment code start at address 2100H. There are 10 bytes, one for each digit 0 to through 9. These are common anode active low ports like C0 for 0, 0F, F9 for 1, A4 for 2, similarly 9049. Okay. For the hardware setup, we used the 8085 trainer kit containing the 8085 CPU, 8255 PPI, 2 KB RAM, and hex keypad, the ETDI 7 segment display module with 4 digits, a regulated 5-volt power supply cable of at least 300 milliamperes, 150 for the 8085, 30 for the 8255, and 105 for the display, and 220 ohm current limiting resistors, 1 per segment. Experimental procedure had 6 steps. First, we connect connected the EDDIS module to 82551 port connector using the 26-pin FRC, which is flat ribbon cable, ensuring pin 1 to pin 1 alignment. Second, we verified connection with a multimeter before applying power. Third, we entered the program bytes into the memory starting at 2000 H using the hex keypad. Fourth, we entered the segment code table at 2100 H. Fifth, we verified all memory entries by examining memory addresses 2000 H through 26F H and 2100 through 2109 H. Sixth, we set the program counter to 2000 and pressed uh, execute. Uh, this From this slide to other slides, this shows complete machine code table, the actual hex byte that are entered from trainer kit's memory. Table 1 covers the main program from addresses 2000 H to 203F H. We can see this table. This is 1 second delay call, and this is we are shifting our 8 bits one by one using shift register. And this table 2 covers the delay subroutine from 2050H to 2066H. We can see this. And this is our segment code table where in which we are entering our each digit 8 bits code from 2100H to 2109H. You can see here. This is our 8085 microprocessor trainer kit. We have connected our 7-segment display with this FRC cable, and we are also connected its power supply with microprocessor. We can see there are 4 such laid here. We have written the code for good, and we modify this code for this and converted it into a counter. This is whole connection. Okay, so this is our main video where I will show the counter. I have used only this first display. These are the garbage value which is showing. We can see here it is showing, it is counting from 0 to 9 in a loop. These are garbage value. I have only used this segment. So the result was were fully successful. Let me go through the observation table from all 10 digits 0 through 9. The correct state segment activated with the correct common anode codes. Digit 0 showed a closed rectangle with the middle bar 0 G off. Digit 8 had all 7 segments on maximum brightness. Digit 9 had all 7 segments on except bottom left E. Every digit matched the expected segment pattern. We can, okay. So these are the real world applications. of the counter architecture that we implemented in the experiment. First, with digital clocks and timers, same counter per digit for hours, minutes, and seconds, but driven by crystal oscillators instead of software delay for accurate timing. Fuel pump meters, a flow sensor generates pulses, each pulse triggering a counter increment. The same architecture but hardware triggered instead of software. Industrial counter on production lines, the 8085 interrupt pins replace the software delay as the event trigger, counting physical objects passing a sensor. Medical equipment, patient drip rate monitors, pulse oximeters, respiratory rate displays all require the same kind of microprocessor precision we demonstrated here. And perhaps most importantly, Arduino, PIC, STM32 microcontrollers all use exactly the same input-output port model we learned here. The 8085 is a transparent prototype that makes these concepts visible. Thank you for your attention. I'm happy to present this video to you people.